So I'm going to talk about dot products. So the dot product is just if we look at some vector v1 equals x1, x2 all the way up to xn, and v2 equals y1, y2 all up to yn, then basically the dot product v1 dot v2, which is this is the symbol of the dot product, is equal to x1 y1 plus x2 y2 plus xn yn. So you just multiply each component together and add them together. And what should be interesting about this is a relationship between the dot product and the geometric properties of these vectors. So geometrically, and you can prove it with the Pythagorean theorem basically, is that v1 dot v2 is equal to the magnitude of v1 times the magnitude of v2 cosine theta. So what's interesting about this is that usually, you can figure out this dot product very easily and figure out the magnitudes very easily. So you can easily find out the angle between the two vectors. That's what this theta is, by saying that theta is equal to v1 dot v2 divided by v1 v2, and then what you do with that entire thing is inverse cosine. So what's very interesting is that you can see that when theta is 90 degrees, or theta is equal to pi over 2, you can see that cosine theta, you can see that cosine theta equals 0. So then v1 dot v2 equals 0. Well, what does that mean if the theta between v1 and v2 is pi over 2? Well, basically what that means is that they're orthogonal to each other. So if I look at v1, v2, there's a right angle between them, right? Because if this is theta, and theta is equal to pi over 2, which in degrees is 90 degrees, so that would mean that they're orthogonal. So what you can do is you can actually, if you're really interested, is you could do like a lot of interesting things with the previous expression here to not only figure out just for some two vectors what's the angle between them, but you can also figure out, well, if I pick certain components for certain vectors and I leave a couple out, you can actually start making linear systems off that to try to figure out the components you left out, such that you're guaranteed that they're orthogonal to each other. So there's a lot of cool stuff you can do here. This is the dot product. It's very important in more general terms because the dot product is a very special form of an inner product, which is I'll talk about later, but inner products are extremely important, for a lot of, I guess I'll mention now, sort of optimizing. Inner products are very important for optimizing. So overall, dot products for now are just sort of an operation, but their generalization inner products are really the meat and potatoes of a specific area of linear algebra. So that's all for now.